Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So, without any further ado, let's get started. Today we are going to talk about a new topic which is related to sampling and its application in data mining. So, let us read the question first. You are given a set of m objects that is divided into k groups, where the ith group is of size m. Now, since it is related to the group I, so it is called m, and in subscript it is I. If the goal is to obtain a sample of size n smaller than m, what is the difference between the two sampling schemes? Assume sampling with replacement. First one is we randomly select n times mi over m elements from each group. The other approach is we randomly select n elements from the dataset without regard for the group to which the object belongs. Right. Now, the question in itself may seem simple, but when we actually try to understand that what are we going to find, it may become a bit more involved and detailed. Okay. So, for that, first we will look at what is sampling. So, sampling is basically choosing a subset of objects from a population to estimate population properties like mean, proportion, distribution, right, or to train or validate models when using the full dataset is costly. So, the initial part of the sampling definition comes from obviously probability and statistics and that class, and as we go to the second part of the definition, which says or to train or validate models when using the full dataset is costly. This is the data mining part, right. So, in whole sum, sampling lets us use the population properties instead of using the entire population. Okay. Now, we will look at where sampling is used. So, we must have seen all these things, surveys, right. We get invited to do surveys, we get them from colleges, external sources as well, right. So, these all things, right, are sent to specific people or a broader set of people just to get an idea of what the population is thinking or has the opinion about, right. The another part is A/B tests, right. Even when an app is launched, the A/B tests are performed over a small set of public, right, not in the entire user base, right. So, why? Because it lets us confirm what the design or UX would look like before rolling it out to the masses. Then there is data mining and ML, training, validation, test splits, and class balancing. All these things can be done on the population itself, but again, training, validation, test splits, all these things do take significant amount of time and cost as well, right. So, in order to save on that as well as preserve the core properties of data, we emphasize on sampling the population accurately. Then there is quality control and manufacturing, right. So, if let us suppose we have a facility for some physical goods, right. So, the quality control and manufacturing part is handled by sampling only. We cannot take the entire batch and put it into the testing phase, right. We take a sample and then use it to ensure the quality. Then there is web analytics, log analysis, and streaming data. All these different paradigms do the same thing. They take a sample, analyze it, and then make a remark on what action needs to be taken over the entire population. Okay. Now, we will look at some of the core knobs of sampling which help us determine the different types of it as well. One is with or without replacement. So, in simple terms, can the same item appear multiple times in a sample, right. So, that is meant by with or without replacement, right. So, if in the population there happens to be no shortage of samples or the population stays the same when you bring out the sample, it means that we are dealing with sampling with replacement, right. Then there is design. So, it can be simple, random, stratified, cluster, systematic, PPS, probability size, right. So, all these different types of sampling designs are also in use. Now, we will compare the two schemes of the given problem. So, first, which says select Ni which equals n times mi over m elements from group, that is proportional per group count. As we can see, mi is the number of elements in that group over the total number of objects existing, right. The next scheme is select n elements from the full data set ignoring groups. So, imagine if we had no groups and then just mix bag all these things, then it is scheme 2. Next, we come to a little trivia about what are these two schemes actually called, just so you know. So, the first scheme is proportional stratified sampling, and it is a special case of stratified sampling where allocation is proportional to the stratum size, group size. Next is simple random sampling with replacement, which is also called SRSWR in acronym. Next, we come to the actual difference between these two. First difference comes as how many from each group, right. So, talking about the first scheme A, we will call it A from now. The counts per group are fixed exactly, which is n times of mi over m. Then there is the B scheme. Here the counts per group are random, and if it is random, then we can use the multinomial theorem. So, from n1 to nk, these are the number of items from each group. We have the multinomial expression of n where pi equals mi by m. So, if we want to enumerate the number of elements and see what the average looks like, so E, that is the expectation, so average equals n times of mi over n, right. But they will fluctuate with a certain parameter, which is the variance in ni, which equals n times mi over m times of 1 minus mi over m, right. You can relate this to the binomial theorem when applied on probabilistic models. Okay. Now, the key takeaway from this particular demonstration up here is that the scheme A will always guarantee representation of each group. Now, the scheme B will match scheme A in this department only on average, right, with randomness around it. As we saw in this demonstration, that B will always take all the groups as 1. Next, we come to per item inclusion probability, right. So, it is also called at least once criteria. So, for an object in group I in the scheme A, the probability of that object to lie inside the sample is 1 minus in bracket 1 minus 1 by m of I over ni, right. The ni does come from the sample size that we are taking and thereby depends on that. So, for each group it is subject to change, and if we make it in a much simpler manner, like generally we want to keep only one variable that is dependent on I, right. So, if we want to change ni into mi, then we can do like this 1 minus in bracket 1 minus 1 by mi raised to the power of n times mi over m, right, which is nothing but ni as we saw in the equation above or was given in the question as well, right. So, this was scheme A. Now, we take the explanation for scheme B. So, the probability that any object exists is going to be all symmetrical, right, and will depend on the sample size that we are taking. Hence, 1 minus in bracket 1 minus 1 by m raised to power n. So, it might seem similar, but these are generally not equal, though they become close when m is quite large. Remember, m is the number of objects, right. So, if that has become large enough so that n and m are likewise such in large numbers that the group distinction doesn't really matter much. So then this might happen, because we know there are different approximations of Taylor series associated with such expressions, right? So that might come into the picture. Next, we see the similarity a bit. Both designs give each object the same expected number of hits, that is n by m, right? But the chance of appearing at least once has differed in both the cases. So the third difference is estimator variance. So in this one, the reason why we stratify will come into the limelight. Suppose each object has a value, right? Let's say income or defect indicator, right? And we estimate the population mean. Okay. Therefore, for the second scheme SRSWR, the variance in that case, this is y bar, so let me change it a bit, is nearly equal to s square over n, where s square is the population variance, right? This is quite simple, we have come across this previously as well. Stratified with proportional allocation, which is scheme A, this time the variance of the stratified mean is nearly equal to 1 over n summation of 1 to k, which is the number of groups, mi over m times si square. Now, just for you to guess what is si, si will now be the within group variance, right? So let's suppose the group is in itself is a population, so in that population what is the variance is denoted by this, right? So si square is the within group variance. Next, we see that if groups are internally homogeneous, meaning that the groups by itself are well defined and they in themselves hardly have any differences, this will lead to a smaller SI, right? But differ from one another. What does this mean? Group A is very similar in itself, right? All of it is very similar to itself, and then we have B, right, which is definitely different from the group A, right? In that manner, we can say that summation of mi over m times si square will be less than s square. Why? Because this particular entity will always be less than 1, right? And we are summing it up over the product si square, hence it will be less. Stratified sampling now, as we saw here, will have lower variance than the simple random sampling method, right? So this is SRSWR, I hope it's right, and this is the stratified okay. All right, next we go to a worked example for this one, because obviously numbers and examples do clarify a bit, right? So for that we'll keep m, which is the total number of objects, as 1000, 3 groups of sizes m1, m2 and m3, 100, 300 and 600, and n, which is the sample size that we want, right? So in A, proportional stratified, the number would be quite simple, which is mi over m, hence 10, 30 and 60, right? 100 by 1000, 300 by 1000 and 600 by 1000. For the simple random sampling, we have n1, n2, n3, which is going to be multinomial of 100 and 0.1, 0.3 and 0.6, right? So in that case, the mean of n1 would be 10, right, which is n times of mi over m. Now it can fluctuate with the standard deviation of n1, which is under root of 100 times 0.1 times 0.9, as we saw in the formula above. I am just putting in the values, so which comes down to be 3. right? Now group 1, this was group 1, so group 1 will often be 7 to 13 instead of exactly being 10, right? So in group 1 we can have either 7 elements, either 13 elements, or in between, instead of having 10 exactly all the time, right? So small groups are the most volatile in this scenario. As the number of elements in that group increase, this will become more and more stable. Then we come to another point which says if the group means differ a lot, but each group is internally consistent, scheme A will give you tighter confidence intervals and more stable model training, right? Because the clusters, if you think about it, will be more well formed, so the classes will get labeled much easier. Now we'll look at one more thing, which is how to implement this sort of thing in the actual data pipeline. Okay. So for that, first we calculate Ni, which is n times mi by m. If we get non-integers that are arise from this operation, we do randomized rounding. Now what's that? First we floor all Ni, right? Do the floor operation for all of them. Then distribute the remaining n minus summation of floor of Ni to all the largest fractional parts, right, which is the sample size that is remaining. Then we sample Ni with replacement inside each group I, for because this needs to be a proportional measure, hence we will do the sampling with replacement inside the group. For estimation, weight each stratum's groups sample mean by Wi equals mi over m, which is just the scaling factor, nothing else. Hence the mean would be mu cap, it is the notation here, of summation of I 1 to k Wi times yi bar, right, which is the mean for that particular stratum. All right, so that's how you actually implement this one. Now coming back to the problem again, we'll now look at the inference. So both the schemes which we saw are unbiased for the population mean, right? They don't bother what the population mean is, but in the scheme A it is given the right weight, right? In scheme B it is just the random weight as per the number allotted, but in A the weights are just right. Then there is the key difference in variability in group representation, fixed in A and random in B. Then when groups are meaningfully different, right, if the groups do possess different properties, which is most likely going to happen, then we will say that A usually reduces estimator variance as we saw above and improves the fairness and coverage of the sample. But during the process or during the simulation, if we discover that some of the properties have become irrelevant over time and no structural difference is found now, we do not need to go for A then, right? We just can simply go via B, which is simpler, and since the properties don't matter to our application then, so it would be a simpler approach. So now we'll see some of the modifications that are commonly used with the sampling methods. First is disproportionate stratification or oversampling. If I want to explain in simple terms, we deliberately take more elements from rare or critical strata, right? So the minority class in the classification is used a lot, and use the inverse probability weights in estimation and training. That is also one approach. Then there is name and allocation. So in that one we choose Ni somewhat proportional to MISI, right, more for the variable strata to minimize the variance that we get in the end. Then there is without replacement versions to avoid the duplication scenarios when n is not tiny, and it is quite common in surveys as well. Then there is weighted SRS, right. we draw probabilities proportional to their importance. So this is quite common. Then there is reservoir training or reservoir stratified sampling, which maintain some proportional samples of data from the data streams. And then at the last we have stratified k-fold CV, and this is mostly taken into count with the event of class balance or class imbalance problem. Okay, so that was kind of the overview of this problem. And if you want to know more about these modifications and want to read more about such problems or practice more such problems, then you can find so in the Sigma Solver community. To join the community, you can simply click the link in the description given below. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.